This empirical study I want to share is about congested subway transfer traffic patterns. This study tries to find problems of moving line, then understand the factors that interfere with the moving line. Finally, we showed some design proposals for verification by using Unity to make design simulation. The Taipei MRT station, which has an average of 308,000 passengers per day, is also the largest station in Taiwan. Underground second-floor interchange hall is our research base, which is the most complicated place passengers transfer often. Past studies found that there will be more conflict and interference in the 90-degree angle of the road. Also mentioned that B2 has a higher flow density than the other floors of Taipei Station, so we choose this place as the research base. This study tried to discuss as passengers moving line, hardware facilities and their transfer process and other environmental objects in space to explore the relationship between them. Then discuss their transfer route from start to end point, with their reaction from interference behavior at B2 interchange hall. Based on what we observe, making some shunt plans by stimulation to verify which plan is better. As we knew, the primary goal of passengers is to have a clear route and to reduce the interference of walking. In MRT stations, we often see the use of shunt fence to guide passengers to walk on the moving line, to reduce conflict, but the ratio of space capacity to crowd flow should be taken into account to avoid queuing. In a crowded situation, pedestrians tend to choose the shortest route, but not the fastest route. Passengers try to slow down when disturbed in the same direction, change their direction when interfered in the opposite direction. We use non-participant observation, chose B2 of MRT Taipei Station as a base to observe passengers' routes in rush hours. I used the camera and followed the passenger from the start to the end point, observe how they walk along the way, where the disturbed behavior occurs, and where they end up. Total 320 passengers. Start point is an entrance to B2, including upward escalator to B2, entry gates, stairs. Endpoint is an exit from B2, also including downward escalator from B2, entry gates, stairs. Blue area is Bannon Line, red area is Tansuzanine Line, 2 green areas are gates. 6 start points we chose: U1, U2, U3, U4 of Bannon Line, and U505B, U6, a U6B of Tansuzanine Line. Each start points have its own upward escalator. 6 endpoints all have downward escalator. There are D1, D2, D3, D4 to Bannon Line, and D5, D6 add 6B to Tansuzanine Line. Gates include start and end point. We use E to represent entry and exit gates as E1 and E2. Stair is endpoint, S1, S2, S3, S4 to Bannon Line and S5, S6 to Tansuzanine Line. So we did 3 non-participant observation as below, then tried to make 3 stimulation shunt plan by Unity. Let me talk about what we found from 3 non-participant observation. When we observed passenger flow at each starting point, we found of the 4 starting points of the Bannon Line, we found that passengers are almost from U2 and U3, where diversion is not good. At the beginning of the Tamzu line, the number of people at the beginning of the U6 line is relatively large. There was no difference between passengers arriving from E1 and E2. We found that U2, U3, U5 and U5B The flow of people lasted for a long time and the interval was short. The crowds at U6A and U6B of Tamsu Line and ticket gates E1 and E2 were uninterrupted during peak hours. The blue Bannan line has a single shift about 300 people. The red one is the Tamsu line. When the crowds on both lines arrived at B2, they almost all overlapped, although the number has decreased over time. When passengers are shuttling between B2 at the same time, it will cause congestion. So we found a significant difference of flow at the starting point of Bannan line. The crowds will overlap. At the beginning of Bannan line, the flow of U3 people is the largest. The largest flow of U6 people occurred at the starting point of Tamsu Zanai line. The larger the traffic at the starting point, the longer the duration of the flow. Second observation is about choice of destination preferences and transfer moving lines. The first one is the passengers coming up from Bannan line to transfer or leave the station. The endpoint D5 is in the center of the field, and there is no significant difference in the number of people at each starting point. The endpoint D6A, you can see that most of the passengers starting from U1 and U2, U3 and U4 passengers prefer D6B. Next is the passengers coming up from Tamsu Zanai line to transfer or leave the station. D1 and D4 have few choices. The endpoint D2, mostly passengers departing from U5 and U6B. The endpoint D3, mostly passengers departing from U5 and U5B. The last one is the passengers coming up from gates transfer to lines. Almost all of the passengers at D1 and D6 start from E1. Passengers at D4 and S5 almost start from E2. Endpoint D5 is in the middle of the field, so there's no difference. Passengers will choose the most direct route. Then we count the number of passenger movements and find out the areas where the lines are most interlaced. The darker color means more people there. T intersection is the most complicated area with moving lines. After all passenger lines have been overlapped, we found that passengers in these two red areas would avoid T intersections. We know passengers prefer to travel through columns to shorten walking paths and avoid crowds. Passengers departing from U4 and E2 are this type. If you look at the moving line from the source of passengers, the green line refers to passengers departing from gates, the blue line refers to passengers from the Bannan line, and the red line refers to passengers from Tamsu line. There is most conflict area. The moving line of E2 is more chaotic than E1, and there is a path conflict at the corner. Similarly, in the black line at the corner, there is also an interlacing of the moving line because of different direction of operation of escalators. So we found passengers choose routes with short distances. T intersection is the most complicated area with moving lines intersecting. Passengers prefer to avoid crowds by shuttling through columns. The location and operation direction of the facility affect the moving line. Third observation is about transfer behavior and distribution. When passengers encounter interference, they change their walking paths and slow down to avoid any physical collision. The starting point U5 have the most disturbed behavior. The most disturbed behavior on the Bannan line is U2, because the starting point of U2 is near the T junction. U6 is the least disturbed at the start of the Tamsu line, where travelers shuttle through columns to avoid crowds. Those who are departing from E2 are the least disturbed, because people from here don't go through areas that are jammed by moving lines. If we overlap 5 disturbed behavior type, it can be seen that most of the acts occur near T junction and left and right escalator corners. The right escalator is disturbed more frequently. So we found, when passengers encounter interference, They often change their walking routes. The number of interference behavior near T junction is the highest. Passenger shuttles through columns to reduce interference behavior. T intersection, escalator entrance, and exit often occur interference behavior. The position of the escalator will affect the interference behavior. After 3 observation, then we did some simulation to evaluate any possibility to make it better. I used the Unity 3D software to control the relevant parameters. We measure the size of the scene, restore the model of Taipei Station and then import it into Unity. Then we set the parameters. Speed setting of the escalator follow national standard rate and regulation. According to previous surveys, the parameters will be set based on the total number of passengers, the percentage of passengers at each starting point, the interval between passengers taking the escalator. Walking paths can be different for everyone. To simulate a traveler's path, we use this formula. Based on the observed route, the route range for a passenger is to use the same route that all passengers have traveled, then draw these paths to Unity. How to define pedestrian walking speed? We used service level for pedestrian passageways to make walking speed dynamic detection. If there's no one in range, the rate is slow down. The average speed range of older and younger people is set to be different. Percentage of passengers choosing to walk on escalators, stand escalators and take stairs based on the simulated period. We know that how many passengers who have entered the station and transferred to another station, and how many of them at each starting point is also known to make setting. The way we set verification standard in shunt plans is trying to know passenger travel time between each starting and end points and the average speed at which passengers travel in each area. We have 3 shunt plans. Plan
A.
Change the route that interferes with moving line. Plan
B.
Change the number of passengers at the starting point. The route is the same as Plan A. Ban and line has significantly different flow at each starting point, so we tried to average flow at each starting point of ban and line. Plan C. Change the direction of the escalator. I swapped the escalators for D4 and U4 as same as D5 and U5. Let's see the results. We used 2 viewpoint as the speed at which passengers travel in each area, passenger travel time between starting and end points to see how it works. Based on the observation, I also simulated a control group. We can see that the 2 areas B2 and F with the lowest rates. When we compare the control group with the 3 plans, we can see Plan C has a higher rate of speed than the control group and other plans, which also means that Plan C can solve the interference of moving line. So we can know the running direction of the escalator is the primary factor affecting the moving line. Then see what passenger travel time between starting and end points. Passengers from here U5A and U5B must pass through the rendezvous area, so I focus on this area to explain what happens. We try to compare control group with 3 plans, see how long they take between starting and end points. We found all plans can reduce the interference of moving line. Plan C is the most effective. So what we found? Based on our observation, the interference of moving lines often occurs around corners and escalators. However, passengers often shuttle through the columns to reduce interference with the moving lines. In Taipei Metro Station, they prefer to choose the route easy to move more than the shortest route. We also found the running direction of the escalator brings a flow of people that affect the smooth running of the moving line. When too many flows are at a specific point, that makes passenger hard to walk. Then, based on Unity simulation, we found adjusting the direction of escalator can improve passenger walking speed, especially plan C is better than plan A, B. All the experimental groups is plan A, B, and C can reduce the disturbance of passengers' rendezvous. There are so many factors that affect the passenger behavior when they are at station, like hardware facilities, passenger line, and flow rate. These factors also vary over time. I think a better way to manage it is to adjust it flexibly to different situations. The use of Unity in this study is one way. I hope it can be used as a reference for further research.